I'm not sure if you did, I don't recall it, but can we go over the rule of 70? I know it's on the board, but I don't know.
We did it, but it's coming up in a couple more numbers, and I did kind of go over it. I wrote it on the board and everything. Okay, I'll get to that, I promise. Remember number 12? You probably learned this in some basic science class earlier on in your career. That your measuring tool decides how good your measurements are, but with a better tool you make better measurements. And with an even better tool you make even better measurements. There is no perfect measurement because there is no perfect tool. Does that make sense to everybody? The public is really pissed that science keeps improving itself because our technology gets better, so we make better measurements, so we have a deeper understanding. This is the nature of science. It's never over. There's no perfect measurement. There's no perfect answer. In number 13, I'd like to use an analogy. You remember that the traditional scientific method says you get a hypothesis and you design an experiment, you perform the experiment, you collect the data, you analyze the data, and whatever. There's a lot of reasons that we can't do that in environmental science. For one thing, we don't have an experimental group. Everybody understands that if we do an experiment to the planet, you can't compare that to the other Earth where we didn't do the experiment, right? We're living in the experiment. And we only get one. We'll have to learn from it as we go, living in the experiment. And it's a complicated system. We don't get to turn off some of the variables. So while we are living in the one experiment, trying to understand it, we realize, oh wait, there's this other variable, and that changes our understanding of it. The planet is complex. There isn't another one for experiments. The time scale is really long. So the best way that we have to understand the experiment is basically by trial and error. We understand the Earth by like, oh wow, when we did that 100 years ago, this started to happen now. I have an analogy for you. I, Jose Caballero, I am going to study anatomy by cutting myself open. I don't know anything about anatomy, but I felt that there are parts in here. I saw a deer get hit once by a car, so I'm pretty sure there's stuff in here. So I guess I'm going to take like a steak knife and a spoon. And this is all the tools I've got. And I don't really know how this works, so we just go for it, right? And then I start like, hey, I wonder what that did. Don't forget that that would be a really sloppy way to understand anatomy. But that's how we are understanding the planet. If I take my lung out, then I'll realize, oh yeah, I needed that for breathing. And now I'm screwed because I'm without a lung. That's how we're learning about the planet. We took out all the predators from the ocean, and now we realize that predators increase diversity. By getting rid of all the sharks, the ocean is dying. Didn't expect that, but now it's too late. We learn after we've done the experiment, and we're still living in that experiment. Very unique science. Anybody want to talk more about why the traditional method doesn't work for science? Yeah, in number 24, it's more of those weaknesses. So the three issues are exponential growth, meaning a lot of our problems speed up, and the more they speed up, the more they grow, and the more they speed up. Exponential growth. So the math is often we understand something at a point where it's growing too fast to control it. Also, there's a lag time. So we might not see the outcome of our actions today for another 400 years. When our descendants, 12 generations from now, can't really tell us about that outcome. Because of the time lag, because the planet's a big, complicated system, we learn a lot of stuff really, really, really late. You know, we found out how to prevent smog after smog had killed unknowable thousands of people. We never knew before because we didn't have that experiment until we'd already done it. Finally, a lot of our changes are utterly irreversible. Like, overfishing is a perfect example. Once all the fish are gone, then we realize, like, oh yeah, that causes this, and that causes that, and that's a problem for us, and this is a problem for us, but now what are we going to do about it? Like, you can break a system. It's like if I'm going to learn about anatomy of pulling out your parts, it's like, oh yeah, the heart kept him alive. But that's past tense now. It's too late to reverse that. Yeah?
I got 424. What was the middle one? Second one?
Lag time. Lag time. A lot of the stuff that we do now will show outcomes in centuries. Yes?
Has there been an alternative to the scientific method?
Yeah, so we have historical records that sort of let us understand what's happening today based on what we know happened centuries ago. So history is really helpful. In a lot of other sciences, it doesn't really matter. Like, I don't need to look at history to understand the parts of an atom. But I do need to look at history to understand environmental science. And also, there's a lot of times that we can just make observations as things are happening that tell us about the entire system. So by watching what happens locally after a volcanic eruption, we understand better how ecosystems respond to change. And one thing that your book may not have mentioned is we can make models of the environment. So we can simplify the system and then understand its function through models. Does that answer your question about alternatives? Okay.
Theory versus model.
Yeah, sure, and that's just a vocabulary distinction.
Right.
A theory is a model that explains phenomenon, and that is supported by evidence. So a theory is only valid if no evidence has disproved it. So, like, the best I understand is that your heart moves your blood around. That's just a theory because I haven't really, seen the blood moving through. And I got to make sure that there's no evidence that contradicts that understanding, then it's still a valid theory. So it's a model that explains phenomena supported by evidence. It has to be an explanation of the things that you're seeing without exceptions to that explanation. Anybody else? So we are done with 1.2. I'd like to talk about 1.3 more briefly. There's just a couple of parts that we should discuss here. First of all, number 3 talks about environmental systems, like the ocean, or like 1.3. 1.3 talks about systems, like ecosystems, like nutrient cycles, like the big complicated parts of our Earth. In the vocab, I talked about open and closed systems. Please remember, those are both theoretical extremes. So one ecosystem could be more open than another or more closed than another, but no system is perfectly closed. You guys realize that our planet is a pretty closed system, but technically we get energy from outside the planet and we get a little bit of space dust from outside the planet. Does that make sense to everybody? It's not perfectly closed. It's pretty tight. Most of the stuff in the planet stays in the planet. But there are still some inputs, and there are still some outputs from our planet. It's pretty closed off, but not completely closed off. You could say a lake is more closed than a river, because the water in the river keeps changing, but the water in the lake changes more slowly. Does that make sense? More closed or more open. But neither can be perfectly closed or perfectly open. There is no perfectly closed system. There is no totally open system. Anybody want to talk about those terms, or is that enough? Yeah.
Can you provide an example of a perfectly closed and perfectly open system?
No, because as far as I understand, we can't. One version of the universe is a closed system.
Okay.
One version of the universe is a closed system. So if we assume that there truly is absolute nothing beyond the universe, then that would be the only closed system. Essentially, all systems are open. Some are just more open than others. The atmosphere is a very open system because everything in the atmosphere is moving in and out of it. Energy moves through it, material moves through it. It doesn't have any inherently stationary items or contained items. Kind of answer your question?
Yeah, I was just wondering, besides the earth or environment, space, if anything. I really they would never ask for an example.
I can't think. If it's not possible, I don't think they would ask you for it. Uniformitarianism confuses my students a lot. Please remember that uniformitarianism, for people today, is a foregone conclusion. There's a term for something that you already know. You know already that if glaciers are moving today, they probably have moved a little tiny bit for millions of years, and that's what shapes canyons and sierras. You know that species evolve historically, so today species continue to evolve. This was a shocking shake-up in the science community back in the day when scientists were all priests. Because back in that time, when one of the only educations came from the church, the basic understanding of science was there was nothing, then a bunch of interesting stuff happened to make everything, and ever since then we've just been chilling here. And some guy said, wait a minute, instead of just turning on the cycles and turning off the cycles, maybe everything that happens now has been happening and will continue to happen. That was a shocking idea because it challenged the religious interpretation of science, which was the leading Western scientific thought. Coincidentally, anybody know the name of the scientist who created the term uniformitarianism? It was in your book. Anybody know the name of that scientist? His name is Charles Lyell. And my son, Toby, that's his middle name, Lyell. It's not up there, but I have a photograph of me and my family in the shadow of Mount Lyell on the Lyell Fork of the Tuolumne River, which is what my boy is named after. Actually, this is him in his river. He's pretty cute. This is also him in his river. I got a bunch of pictures of my girl in her river too. They're both named for rivers in the South. Okay. Anybody want to talk more vocab on 1.3? Sure. Average residence time, I'll do that one first, is the time it takes for something to move through a reservoir. So last night I had to caught some frozen fish, I put it in a bowl, and I turned the faucet to just barely drip. So a drop would go in and a drop would fall out, right? Depending on how big the reservoir is and how often a droplet goes in, each droplet, on average, lives in that reservoir a certain amount of time. And you can calculate that, the volume of the drop versus the volume of the reservoir.
Okay, and so it's like just talking about I don't know, not a physical reservoir,
Not a reservoir in the water sense, but how long radiation lasts in your body after it goes into your body. Or how long food lasts in your digestive system before you get rid of it. That would be average residence time, how long something spends inside something else